Joseph University. I'm here for the presentation of some questions in advanced chemistry for the preparation of Form 6 students year 2025. So this time I'm going to present some few questions based in paper 1. And paper 1, there are 10 questions. So we are going to discuss about these 10 questions, which are essentially giving the basic foundation for the revision of our Form 6 Chemistry 2025. Now the first question, the question 1A says, why does the hydrogen spectrum have a large number of lines even though hydrogen atom has only one electron? Why hydrogen atom spectrum has many lines though hydrogen atom has only one electron? Now, every element has energy levels. So even a hydrogen atom, it has many spectrum lines because it has many or multiple energy levels. Many or multiple energy levels. Multiple energy levels. Energy levels. So that is why hydrogen atom, though it has one electron, still it has many lines in its atomic spectrum. Question number 1B says, Roman 1, calculate the wavelength of light that corresponds to the transition of one electron from n is equal to 4 to n is equal to 2, state of the hydrogen atom. So, B, question number 1B, Roman 1. Calculate the wavelength of hydrogen atom when its electron moves from energy level n is equal to 4 to energy level n is equal to 2. So, from the formula, the reciprocal of wavelength is equal to Rydberg's constant 1 over n1 squared minus 1 over n2 squared. So this is the formula which we are going to apply to calculate the wavelength of an electron when it moves from energy level n is equal to 4 to energy level n is equal to 2 for hydrogen atom. So n, this is the lower energy level, which is equal to 2, and the n2 is a high energy level, which is equal to 4. And the Rydberg's constant RH is equal to 1.097 times 10 power 7 per meter. So this is the constant which we are going to use in order to calculate the wavelength of an electron dropping from n is equal to 4 to n is equal to 2. So if we take this equation, then reciprocal of wavelength 1 over lambda is equal to 1.097 times 10 power 7 per meter into bracket 1 over 2 power 2 minus 1 over 4 power 2. Now if we do calculation, then finally the wavelength, which is corresponding to the transition of electron from n is equal to 4 to n is equal to 2, this gives us this value. So this is equal to 4.86 times 10 power negative 7 meters, or is equal to 486 nanometers. So this is the wavelength of an electron when it moves from energy level n is equal to 4 to energy level n is equal to 2. That is question number 1B Roman 1. Now question number 1B Roman 2. With the results, comment whether the transition in B Roman 1 is absorption or emission. Normally we have two types of spectrum. We have absorption spectrum, in which an electron moves from lower energy level to higher energy level, and also we have emission spectrum when the electron moves or drops from higher energy level to lower energy level. So for this one, because an electron moves from n is equal to 4 to n is equal to 2, so it means an electron is dropping or moving from higher energy level to lower energy level. As a result, this type of emission of spectrum is a emission spectrum. So this is an emission spectrum. The reason is an electron is moving from a higher energy level to lower energy level. Then question number 1 is C. Question number 1 is C. Question number 1 is C. The question number 1 is C. The question says, Roman 1, each element has its own characteristic color. Explain. Each element has its own characteristic color. So the reason why each element has its own electron or its specific or its own characteristic color is because each element has its own structure. Each element has its own structure, and this is one of the applications of atomic spectrum, in which we can identify elements according to the different colors which correspond to their structures. For example, sodium gives a golden yellow color, copper is a blue color. So all these the colors differ because of different differences in structures. Then question number 1 is C. Question number 1 is C, Roman 2. With the aid of their electronic configurations, explain the fact that electronic configuration of chromium and copper violate Aufbau principle. With the aid of electronic configuration, explain that chromium and copper they violate electronic configuration, violate Aufbau principle. So Aufbau principle is the one which describes or explains on how electrons are filled in atomic orbitals. So the law says that filling of electrons in atomic orbitals are following the order of increasing energy. So we're expecting that according to this law, chromium and the copper to obey the law. Instead, the two elements violated this law. The atomic mass of atomic number of chromium is equal to 24, and the atomic number of copper is equal to 29. Now, if we write the electronic configurations of these two elements, you find that for chromium, it is argon, then we have 3D, the 4s1, and here is 5. So instead of filling 4s first, before 3D. So it means that if this could follow Aufbau principle, this could be for S2 and 3D5. Now, according to the rule of thumb that half-filled and full-filled orbitals are more stable, that is why instead of this 3D to carry or accommodate 4 electrons, instead it accommodates 5 electrons, which is the half of its maximum capacity of accommodating number of electrons, as well as 4s also, instead of carrying 2 electrons, now it carries a 4s, which is the half of its maximum capacity. And also for copper now it becomes argon, then 3D10 and 4s1. So it shows that 4s now is a half filled and the 3D is a full filled, and the 2 orbitals are stable, and these 2 configurations violate Aufbau principle. Now, this question number 1 is about the first topic in atomic in general chemistry, that is the atom. Now we go to question number 2. The question number 2 is about chemical bonding, as one of the 2 topics of general chemistry. Now the question number 2A says that compare ionic compounds and the covalent compounds. Compare ionic compounds and covalent compounds. Now here we are going to see the differences between the 2 compounds, ionic compounds and covalent compounds. Ionic compounds sometimes are referred as electrovalent compounds. Now, ionic compounds, then we have covalent compounds. Now, ionic compounds are generally solids. They are generally exist as solids at room temperature, while covalent compounds are essentially gases or liquids at room temperature. They exist in a solid or in a liquid or in a gaseous form at room temperature. Then another difference is that ionic compounds, these are soluble in polar solvents. They are soluble in polar solvents. But they are insoluble in non-polar solvents. Polar solvents are like water, and non-polar solvents are like kerosene, petrol, diesel, etc., etc. But covalent compounds are insoluble in polar solvents, while they are soluble in non-polar solvents. So this is another difference between ionic compounds and the covalent compounds. The third difference is that ionic compounds, because at room temperature they exist as solids, so they have a high melting and boiling points, while covalent compounds, they have low melting and boiling points. So this is another difference. This depends on the existence or the state of the compound. Ionic compounds, because they are generally solids at room temperature, so they have high melting and boiling points, while covalent compounds, because they are gases or liquids at room temperature, so they possess or they have low melting and the boiling points. And also another difference is that ionic compounds, when they are dissolved and they form solutions, their solutions are electrolytes. So when they are in a solution or molten form, they conduct electricity. So they conduct electricity in a molten or in a solution form, in a molten or solution form. While covalent compounds, they do not conduct electricity, don't conduct electricity, whether they are in molten or in a solution form. Because ionic compounds, once they form solutions or they are in molten form, normally they form free ions which are responsible for the conduction of electricity, while covalent compounds, though they can dissolve or they can be in molten form, still they don't carry or they don't have free ions which will be responsible for the conduction of electric current. Now, question number 2b, the bond angles in ammonia, that is 107.3 degrees, and the methane, which is 109.5 degrees, differ, although they both have tetrahedral electron geometry. So methane CH4, or its structure is H, this is H, and then this is H. So this angle is about 107.3 degrees, while for ammonia, which is NH3, but its structure is H, then N, we have lone pair of electrons in H, this is H, so this angle is about 109.5 degrees. Now, why these two compounds, though their geometry are the same, they are tetrahedral compounds, still their angles differ. The reason is because here we have two types of repulsion forces or repulsive forces. For methane, we have only bond electron repulsion, which is weak, as compared to this lone pair bond repulsion. And also on this side, we have lone pair bond repulsion, which repels much these bonding electrons, and they squeeze them or compress them, and they create the larger angle. So the reason is because in methane there is no lone pair of electrons, while in ammonia there is a lone pair of electrons which repels much these bonding electrons, and makes the angle in ammonia to be greater than the one in methane. Question number 2C Roman 1. 2C Roman 1. The question says, nitrogen and phosphorus are group 5 elements. Nitrogen forms trivalent compounds, while phosphorus form both trivalent and pentavalent compounds. Trivalent and pentavalent compounds. That is question number 2. That is question number 2C, Roman 1. 2C Roman 1. That nitrogen and phosphorus are group 5 elements. Group 5 elements. But nitrogen form trivalent compounds only, while phosphorus forms trivalent and pentavalent compounds. Now the reason is that if we write the electronic configuration of nitrogen, This is 1s2, 2s2, then we have 2p3. So this is the electronic configuration of nitrogen, and the electronic configuration of phosphorus is 1s2, 2s2, 2p6, then we have 3s2, 3p3. Now, according to these electronic configurations, in nitrogen we don't have 3 or third energy level. Now, the reason why nitrogen forms trivalent compounds only, while phosphorus forms both trivalent and pentavalent, though both elements are group of 5 elements, is because phosphorus can expand its valence shell. Now, what does it mean by this? Because we have a third energy level, in the third energy level, phosphorus can use its 3D. Now, by using its 3D, during formation of pentavalent compound, it means that it has expanded its energy level. But nitrogen cannot, because it ends up with a second energy level in which there is no d orbital. So phosphorus can expand its valence shell that enables it to form pentavalent compound as compared to nitrogen. Question number 2, C Roman 2. Phosphorus pentachloride hydrolyzes while phosphorus trichloride does not. Phosphorus pentachloride hydrolyzes means it reacts with the water, while phosphorus trichloride does not hydrolyze. Now the reason is phosphorus pentachloride has an empty orbital. Here there is an empty orbital that can accommodate a lone pair of electrons from water, and this enables it to react with the water. Why phosphorus trichloride cannot hydrolyze? Because it does not have an empty orbital in its structure. So when you draw the structure of phosphorus pentachloride, you find that one of phosphorus orbitals is empty that can accommodate a lone pair of electrons from water, and thus reacts with the water. While in phosphorus trichloride there is no empty orbital. That is why phosphorus trichloride does not hydrolyze. Then question number 2 is about chemical bonding, which is a part of general chemistry, as according to A-level syllabus, chemistry syllabus. Question number 3. A. Now this question is about gas laws. Gas laws is a part of A-level chemistry syllabus. It is a physical chemistry topic. Gas laws. Now the first question, question number 3A. A says, how does Boyle's law related to breathing? How does Boyle's law related to breathing? How does Boyle's law related to breathing? So this is one of the daily life's application of Boyle's law. There are so many applications of gas laws, but one of the applications of Boyle's law is the breathing. Now during the breathing, because breathing has two processes. We have exhalation and also inhalation. Now, inhalation means taking in air. So during inhalation, then as according to Boyle's law, which says that pressure is inversely proportional to volume. So it means when the pressure increases, the volume decreases, and vice versa. So in this law, during inhalation, is that the lungs volume, the lungs increase their volume, they increase their volume. Now by increasing their volume, the internal pressure in the lungs decrease. Internal pressure decrease. So internal pressure decreases during the process. Decreases. Now by decreasing the pressure, internal pressure, then it allows the air to enter in the lungs. So this allows air to enter. So allows the air to enter. Allows the air to enter in the lungs. So, and also during exhalation, then according to Boyle's law, lungs volume decrease. So lungs decrease their volume. Lungs decrease their volume because volume is inversely proportional to pressure. So it means the internal pressure increases. So internal pressure increases. Internal pressure increases. Internal pressure increases. As a result, this will force out carbon dioxide gas from the body to come out, and this one is another application of Boyle's law. So this is how Boyle's law is related to breathing. That during inhalation, when we take in air, it means the lungs they have to expand or increase their volumes. As a result, the internal pressure in the lungs decreases, and this allows air from outside or surrounding to enter the body or lungs. And also during exhalation, the lungs volume decreases. As a result, increases the internal pressure that will force out carbon dioxide. That is question number 3A, Roman 1. Roman 2. Charles' law contributes to the designing and the operation of the hot air balloons. You know that hot air balloons, they are used in different purposes, can be used in sports, recreation, and there are so many other applications. But why hot air? And as according to Boyle's, to Charles' law, the law says that temperature is directly proportional to volume. So this is Charles' law. Charles' law, which says that temperature is directly proportional to volume. So it means by increasing the temperature, then you increase the volume. Now in balloons, we know that in order for the balloon to raise or to float in air, it means its density must be less than the density of air. Now, how to make it less dense while it contains the same amount of gas is by increasing the temperature. So that is why we use these hot air balloons. Now, during this process, you find that when the temperature increases, when temperature increases, then volume of balloon also increases. Volume increases. Now, once the volume increases, because this balloon contains the same amount or fixed amount of air, or gas, so it means that its density will be less. So it becomes less denser. Becomes less denser. As a result, this balloon can rise or float in the air. Float in the air. Floating in the air. So this is one of the applications of Charles' law in everyday life. That for hot balloons is that when you increase the temperature, you're increasing the volume of air while you contain the same amount of air. As a result, you make this balloon to be less denser than air. As a result, it rises or floats in the air. Float in the air. Then question number 3b. Question number 3b. Under the same temperature and pressure, how fast will hydrogen gas effuse compared to carbon dioxide? How fast does hydrogen gas diffuses as compared to carbon dioxide? This is according to Graham's law of diffusion or effusion. Graham's law of diffusion. So this is according to Graham's law. Graham's law of effusion or diffusion. Of effusion. Of effusion. Now, effusion is the flow of air or volatile material through a small hole or through a tiny hole. That is Graham's law. And the law states that the rate of effusion or diffusion of a gas is inversely proportional to the square root of its molar mass or its density. That is, rate of diffusion or effusion is inversely proportional to the under root of its molar mass or density. Rate of diffusion or effusion is inversely proportional to the square root of density or molar mass of a gas. But the question is how fast hydrogen gas effuses as compared to carbon dioxide. Now, according to Graham's law, then we apply Graham's law formula, that is the rate of effusion of hydrogen gas divided by rate of effusion of carbon dioxide gas. This is equal to under root the molar mass of carbon dioxide gas divided by molar mass of hydrogen gas. So this is the formula which we are going to apply in order to know by how much hydrogen gas effuses as compared to carbon dioxide. Now we have to get the molar masses. So the molar mass of hydrogen gas is equal to 2 grams per mole, while the molar mass of carbon dioxide is equal to 44 grams per mole. So these are the molar masses of these two gases, of which their effusion rate of effusion are to be compared. So we take rate of effusion of hydrogen gas divided by rate of effusion of carbon dioxide. This is equal to under root of 44, which is the molar mass of carbon dioxide, divided by 2, which is the molar mass of hydrogen gas. So this gives us 4.69. 4.69. So this is the ratio of the rate of diffusion of effusion of hydrogen gas compared to carbon dioxide gas. So therefore, we say that hydrogen gas effuses 4.69 times faster than carbon dioxide gas. So this is how fast hydrogen gas effuses as compared to carbon dioxide gas. Now question number 3C. Question number 3C. The question says In order for a gas-filled balloon to rise in air, the density of the gas in the balloon must be less than that of air. As I said for the first part of this question, that in order for the balloon to float or to rise in air, its density must be less than that of air. That is why nowadays we use hot balloons in order to make the same amount of gas to be less denser than air, as according to Charles' law. Now, question this Roman 1. Roman 1 says, consider air to have a molar mass of 28.96 grams per mole air, and determine the density of air at 298 Kelvin and 1 atmosphere in grams per liter. So here the question is to calculate, to know the density of air. Density of air. Let us abbreviate it by rho. Now, the molar mass of air is assumed to be 28.96 grams per mole. Then the conditions under which this air is existing is that temperature is equal to 298 Kelvin, and the pressure of the surrounding is 1 atmosphere. Now, the question is to calculate the density of this air with the molar mass 28.96 grams per mole, temperature at temperature of 298 Kelvin, and also pressure of the surrounding is 1 atmosphere. Now, here we apply the ideal gas equation. Ideal gas equation is the equation which combines several gas laws. Now, the ideal gas equation says that PV is equal to nRT, where P is the pressure, V is the volume occupied by air or gas, N is the number of moles of air or gas, R is the molar gas constant, and T is the absolute temperature or temperature in Kelvin state. But N, number of moles, is equal to W over capital letter M, where this M is a mass of gas, while this one is a molar mass of gas, molar mass of gas in grams per mole, while this is gas in grams. Then we can now take PV is equal to WRT over capital letter M. Now, rearrangement of this equation will get PM is equal to WRT over V, where W over V is equal to density, the density of gas, this gas or air. So then PM is equal to density RT. So make this density of air the subject of the formula, that is rho is equal to PM over RT. Now, other values are given. This is equal to pressure is equal to 1 atmosphere times the molar mass of air is 28.96 grams per mole, divide by molar gas constant, which is 0.0821 atmosphere liter per mole, then per Kelvin, times temperature is 298 Kelvin. Then finally, the density now of this gas is about 1. The density of the gas, is 1.18. So therefore, the density of this air is equal to 1.180 grams per liter. So this is the density of air, the air used to fill the balloon. So it means if the balloon has density which is greater than 1.180 grams per liter, it will not float or rise in air. It will not float or rise in air. So this is very important to know the density of air of the surrounding where you want to launch your balloon. To launch your balloon, to know if its density is less than the density of air. Now, question number 3, C, Roman 2. Roman 2 says, show by calculation that a balloon filled with the carbon dioxide at 298 Kelvin and the 1 atmosphere could not be expected to rise in air at this temperature. So our task is to show by calculation that on how the air balloon filled with the carbon dioxide at the same temperature and the pressure as the air could not rise in air. So it means to show that mathematically that its density is greater than this one, or greater than the density of air. Now we say that we apply this equation that density is equal to Pm over RT. Now P is 1 atmosphere times the molar mass of carbon dioxide is 44 grams per mole. Then you divide by the value of molar gas constant is 0.0821 atmosphere liter per mole per Kelvin times the temperature is 298 Kelvin. So if we calculate the density of carbon dioxide filled in this balloon, you'll get 1.8. It is 1.8 grams per liter. So this is the density of carbon dioxide. The density of carbon dioxide. Now, if we compare this density of carbon dioxide, it is greater than the density of air. So it shows that if we fill the balloon with the carbon dioxide, then it cannot rise in the air because its density is greater than the density of air. Now question number 4. Question number 4 is about colligative properties of solutions. Colligative properties of solutions. Now, question number 4A, Roman 1. How does the vapor pressure lowering affect cooking processes? How does vapor pressure lowering affect the cooking processes? So, we know that in colligative properties, we have 4 colligative properties of solutions. We have vapor pressure lowering, elevation of boiling point, depression of freezing point, as well as osmotic pressure. But the other 3 colligative properties are affected or depend on the lowering of vapor pressure. Now the question for A Roman 1 says to explain on how vapor pressure lowering affect cooking processes. Now if we lower the temperature or the vapor pressure, it means that the boiling point will be elevated. Now if the boiling point will increase or raise, it means that the cooking process will be fast. So we say that lowering of vapor pressure then elevates. It elevates or raises the temperature of boiling point boiling point. As a result, the cooking process will be fast. Cooking processes will be fast. So by lowering of vapor pressure, normally it raises the temperature. For example, if you are cooking, let's say, vegetables or meat, if you add salt is one of the solutions that can lower the vapor pressure of a solution or liquid, but it raises the boiling point. So the answer here is that if you lower the vapor pressure during cooking, it means you are raising the boiling point. As a result, in the cooking process will be fast. Then question number 4, A Roman 2, describe the practical applications of boiling point elevation in automobile engineering. Explain or describe the practical applications of boiling point elevation in automobile engineering. Now, we have these solutes which we call them as antifreeze, or for example, ethylene glycol. Ethylene glycol is one of the solutes which are added in the radiator water in order to raise the temperature, in order to raise the boiling point of water. So in hot climates, this enable the boiling point of water to increase. As a result, this will avoid the overheating of the engine. So the reason here, or the application here, is the addition of or elevation of boiling point. Elevation of boiling point. Boiling point here is done by adding solutes, which raises or elevates the temperature, then to overcome or to avoid overheating of the engine. So this is very important in automobile engineering. Then question number 4B. Question number 4B. Now question number 4B says that before refrigeration was common, many foods were preserved by salting them, having heavily, and many fruits were preserved by mixing them with a large amount of sugar. How do salt and sugar act as preservatives? How do salt and sugar used as preservatives? This method is still common in some areas, especially in rural areas, where salting of foods like meat is still applied for the preservation of these foodstuffs. So this is the application of osmotic pressure and osmosis. Osmotic pressure and osmosis. So say that by salting the food heavily, for example, fish or meat, or by mixing fruits with a large amount of sugar, is to lower the internal osmotic pressure of the bacteria cells, which will result into dehydration and make bacteria to die. So we say this causes the internal osmotic pressure. Internal osmotic pressure of bacterial cells cells to be less than external pressure, to be less, that makes cells, bacterial cells, to dehydrate in the dye. To dehydrate and dye. So this is one way of preserving foodstuffs like meat, fish. Then we can salt heavily, and this through osmosis, the bacterial cells which invade the foodstuff, they dehydrate. Then during dehydration, these bacterial cells die. As a result, the foodstuff remaining safe. The foodstuff remaining safe. So this is one of the applications or practical applications of colligative properties. Now, C. Question number 4C. If a solution containing 30 grams per liter of organic compound has an experimental osmotic pressure of 0.0124 atmosphere, calculate the molar mass of the compound at 298 Kelvin. At 298 Kelvin. Still, we are under the applications of colligative properties, and the one of the colligative properties we are applying in this calculation is osmotic pressure. Now, according to the general equation of osmotic pressure, that pi V is equal to nRT. Or if we take pi is equal to nRT over V, now this N over V is equal to concentration, or we can take it as a, so this is molar concentration, molar or molarity of that particular solution, But in this question, we are given the mass, volume, temperature, as well as experimental osmotic pressure. So as a result, if we take N is equal to W over M, where this M is the mass of solute dissolved, and this one is its molar mass of solute. And our solute here is an organic compound. Given. So this is there. So we can now modify our equation and become pi V is equal to W RT over M. And the question is to calculate the molar mass of the organic compound. Rearrangement of the equation will be pi, then M. This is equal to W RT over V. But W over V is equal to density. Now, because the organic compound given is 30 grams per liter, so this also can be defined as the density of this solution. So the equation now becomes pi M is equal to density RT. Now molar mass is equal to density RT over osmotic pressure, which gives us, so the density here is 30 grams per liter, then R is 0.0821 atmosphere liter per mole per Kelvin times the temperature, which is 298 Kelvin. This is the absolute temperature divided by osmotic pressure, which is 0.0124 atmospheres. So finally, the molar mass of this organic compound, is equal to 59,191. It is 59,191 0.45 grams per mole, or you can say this is equal to 59.191 kilograms per mole. So this is the molar mass of the organic compound. This is the molar mass of organic compound. And normally the osmotic pressure is mostly applied in the determination of molar mass of large molecules. Large molecules like proteins or any other organic compounds. So this is the method that can be used. That is why even the molar mass here is very large. It shows that this compound is a large molecule. It can be a protein or any giant molecule or complex structure of organic compound. So this is how the osmotic pressure is one of the colligative properties of solutions can be used to determine the molar mass of a compound. Now question number 5. Question number 5A. So with the question number 4, as I said, this is the question about colligative properties of solutions. Now question number 5, this is the question about energetics or thermochemistry. Energetics also is one of the important topics in our everyday lives, as it is used in cooking, in operating engines, and so many other processes, even in geographical and weather regulation, climatical regulation, etc. Now question number 5A, Roman 1. Question number 5A, Roman 1. Now the question says, why is it important to consider the specific heat capacity of materials when designing thermal insulation for buildings, materials, or vessels? That when engineers are designing building materials or vessels, why is it necessary to consider the specific heat capacities of materials to be used? Why is it important to consider the specific heat capacities of materials used? So here we say that the specific heat capacity is the amount of heat energy required to raise the temperature of a unit mass of that particular material by 1 degree centigrade. So it means that when we consider the insulators, or if we want to manufacture different vessels, for example, cooking vessels, so it is very important to consider their specific heat capacities. So here the answer is materials with the high specific heat capacities. With the high specific heat capacities, normally they lose heat slowly. Not only losing heat slowly, also they gain heat slowly. For example, wooden materials. Wooden materials are good insulators. Why? Is because of their high specific heat capacities. So now when you are as an engineer to design the building material, so you have to consider the specific heat capacity of material. And also if you are planning to manufacture, for example, cooking vessels, you have also to consider the specific heat capacities. Because for metallic materials, for example, which mostly are used to make cooking vessels, they must have low specific heat capacities. So it means that they can conduct or gain heat easily and lose heat easily. So this is why during manufacturing of insulators or vessels, the specific heat capacity is very important to be considered. Another question, that is question number 5 A Roman 2. When a solute dissolves in water, the container containing the solution gets colder, explaining whether the process is an exothermic or endothermic. A good example is, for example, when players or if someone get injured, then we can use this, we call them as a cold or hot packs. And cold or hot packs, these are the materials which either lose or gain heat. Now, if you take, for example, ammonium nitrate, for example, ammonium nitrate, which is commonly used as a cold pack. A cold pack. Normally, this one, it absorbs the heat during its dissolution. Now, if it during dissolving process, then the temperature lowers, we say that the process is endothermic. So it means the solution or the solute or material that is dissolving, and if it lowers the temperature and the solution becomes colder, it shows that the process is endothermic. So it means this solute during its dissolution process, it absorbs the heat from the surrounding, and its surrounding is this solution. So the process is endothermic. The process is endothermic because the solute absorbs the heat from the surrounding. Then question number 5b, B says the specific heat capacity of water is 4.2 joule per gram per degree centigrade. How many joules of heat must be added to 1 gram of water to increase its temperature by 10 degrees centigrade? So here the specific heat capacity of water is given, which is 4.2 joule per gram per degree centigrade, and its amount is 1 gram. Now the question is, what amount of heat energy will be absorbed by this 1 gram of water and to raise its temperature to 10 degrees or by 10 degrees centigrade. So here we apply the formula that quantity of heat is equal to mass times the specific heat capacity times the change in temperature. So M stands for mass of the material. In our case, is 1 gram of water. C is the specific heat capacity of material. In our case, this is 4.2 joule per gram per degree centigrade, and the delta T stands for temperature change. And according to our question, the temperature change is 10 degrees centigrade. So the quantity of heat absorbed by 1 gram of water, which rose this temperature by 10 degrees centigrade, is equal to 1 gram times 4.2 joule per gram per degree centigrade times 10 degrees centigrade. So here we get 42 joules. So 42 joules of heat energy will be required to raise the temperature of 1 gram of water by 10 degrees centigrade. Then we go to question number 5C. Question number 5C. The question says, given the heat of the combustion of ethane, hydrogen, and ethane are 1.42, 286.9, and 1.57 kilojoules per mole, respectively. Calculate the heat change for the formation for the following reaction at 78 degrees centigrade. Now the reaction is ethane gas reacts with the hydrogen, 1 mole of hydrogen gas to form 1 mole of ethane gas. So this is ethane gas. This is a hydrogen gas, and this is ethane gas, Now the question is to calculate the enthalpy change of this reaction. So this reaction also can be known as a hydrogenation of ethane. But we are given the standard enthalpies or heats of combustion of these three materials. And normally, combustion is the exothermic process. So during combustion, heat energy normally is given out. So to write this, first we have to write the equations for the combustion of the three materials. The first one is the combustion of ethane gas plus oxygen gas. Then the products are carbon dioxide gas. Here we have 2 moles plus water. This is a liquid. So the enthalpy change here we have 2 carbon, 4 hydrogen. Here is 2, so as to get 4 hydrogen. Then we have 2 oxygen atoms. So the total is 6. So here is 3 oxygen atoms. So the enthalpy of combustion, of ethane is minus 1.42. It is equal to minus 1.42 kilojoules per mole. Then another one is the combustion of hydrogen gas. Here is plus a half mole of oxygen gas. Then you get 1 mole of water liquid. Then the enthalpy of combustion is equal to minus 286.90 kilojoules per mole of water formed. And then the last one is the combustion of ethane gas, then plus 7/2 oxygen gas, that is the 3.5 moles. Then you get 2 carbon dioxide moles plus here is 3 water molecules. Then the enthalpy change here is minus 1.57 kilojoules per mole. So these are the three combustion equations for the 3 materials. But the question is the hydrogenation of ethane to get ethane. So here we have to reverse equation number 3. So let this be equation number 1, equation number 2, equation number 3. Then we reverse equation 3, equation 3, then add the 3 equations, and according to thermochemical equation rules, normally when you reverse the equation, then the amount of energy change will remain the same, but its sign will change. Now because here we have a negative energy, then or negative sign, it will become positive. So we take equation 1, which is a C2H4 gas plus 3 oxygen gas. Then you get 2 carbon dioxide gas plus 2 water liquid. Then the enthalpy change is equal to minus 1.42 kilojoules per mole. Then another one is a hydrogen gas plus a half oxygen gas. Then you get 1 mole of water molecule. That is enthalpy change. Here is minus 286.90 kilojoule per mole or per hydrogen combusted. And the last one is 2 carbon dioxide gas plus 3 water molecules. Then you get 1 mole of ethane gas. plus 3.5, that is 7/2 oxygen gas. Then because we have reversed the equation, now this sign will change and they become positive 1.57 kilojoules per mole. Now after that, we add our three equations. Then we cancel out those items which appear on both sides and also in the appropriate number. So here we have 2 carbon dioxide, this and this one cancelled. We have 3 so here we have 3.5 oxygen gas, 3, then half. Here we have 3.5. Then we have 3 water molecules, 1 water molecule plus 2, 3 water molecules. So finally, if you add the 3 equations, then you will get the required equation, which is CH2, then 4 gas plus hydrogen gas. Then here you get ethane gas, and the envelope change. This is equal to our answer now becomes our answer is negative 286.75. So it is negative 286.75 kilojoules per mole. So this is the energy change for the given reaction. So this was the question about energetics. Now we go to question number 6. Now question number 6. This is the question. Question number 6 is about inorganic chemistry. That is about selected compounds of metals. Now the question number 6a says both aluminum and Ni3 carbonates do not exist. Explain. The question is to give the reason on why aluminum and Ni3 carbonates do not exist. Now aluminum, the reason is that aluminum and Ni3 ions are very small. They have small cationic sizes. Now because of their small ionic sizes, once they are approached by carbonate, instead of reacting and they form the carbonate, they break or destroy or break down the carbon dioxide carbonate into carbon dioxide and the other products. So we say the two carbonates do not exist because of small cationic size that destroys carbonate ions instead of reacting with. So that is the reason on why aluminum and Ni3 carbonates do not exist. Now question number 6b. The question says explain the following observations. These are chemical observations. Then Roman 1. Observation Roman 1. Lead 2 chloride is slightly soluble in a diluted hydrochloric acid. But yet it is quite soluble in concentrated hydrochloric acid. We know that lead chloride is slightly soluble in water. Now when we say diluted hydrochloric acid, it means either acid containing large amount of water, which meant this lead 2 chloride to be slightly soluble in a dilute hydrochloric acid. But the question says why this lead 2 chloride is soluble in a concentrated hydrochloric acid. So this is a concentrated hydrochloric acid, concentrated. Then once lead 2 chloride is mixed with the concentrated hydrochloric acid, it forms a complex. That is the lead Cl4. This is -2. This is the aqueous. So the reason here is because of formation of complex. Most of complex compounds are soluble. So to dissolve the 2 chloride, we can add concentrated hydrochloric acid, which will end up with the formation of a complex that dissolves. Then Roman 2, aluminium hydroxide precipitate is soluble in excess sodium hydroxide. Aluminium hydroxide precipitate means aluminium hydroxide is a solid. It is insoluble or slightly soluble in water, but it dissolves in excess sodium hydroxide. This is one of the applications of qualitative analysis. In the qualitative analysis, normally we can use sodium hydroxide as one of the reagents which can identify different cations. Now the question is why aluminium hydroxide is, this is a precipitate. But if we add excess sodium hydroxide, then we are going to form an aluminate. Aluminate is soluble in water, so this forms aluminate. This will form aluminate. OH, here is 4, then -1. This is aqueous. So we say that, or we can write it as aluminium hydroxide precipitate, that is a solid, plus sodium hydroxide aqueous. When it is in excess, then you get sodium aluminate. H, here is 4, then aqueous. So we say that aluminium precipitate is soluble in excess sodium hydroxide due to formation of complex. The reason is formation of aluminate complex. So this is one of the procedures in the qualitative analysis in which aluminium can be differentiated or distinguished to other cations by using sodium hydroxide. Then question number 6C. Question number 6C. Question says uses of metal nitrates. Uses of metal nitrates in everyday life. Give 5 uses of metal nitrates in a daily life. Uses of metal nitrates in everyday life. One of the uses, metal nitrates can be used as fertilizers. They can be used as fertilizers. For example, potassium nitrate or sodium nitrate. This can be used, and the nitrates are nitrogenous fertilizers. Then another one is that they can be used as explosives. For example, ammonium ammonium nitrate. Ammonium nitrate is one of the explosives. So explosives can be used in mining and in other places. So that is one of the application or manufacture of explosives, and also for medication, e.g. heart pain, for medication, also for medication. So in health set also medication, for example, to remove or to release heart pain, nitrate also can be used, or they can be used for as food preservatives, for food preservation, for food preservation. For example, potassium nitrate can be used as a food preservative, to make the food substance to stay for a long time, and also can be used as a rocket propellant and a fireworks in a rocket propellants, and also fireworks. So they produce large amount of heat energy that can enable launching of rockets, and also toothpaste ingredients as one of toothpaste ingredients. Is one of the ingredients of so these are some of applications of metal nitrates in a daily life. Now we go to question number 7. So question number 7 is about soil chemistry. Question number 7 is about soil chemistry. Question number 7. This is the question about soil chemistry and environmental chemistry. Now, question number 7a explaining the significance of soil pH, the importance, the role played by soil pH. Why soil pH is important? Now, plant nutrients, the availability of plant nutrients are determined by several factors, but one of the factors is the soil pH. Because the soil has two parts. It has soil solution, in which the plant nutrients will be available for plant absorption, and also soil colloid. Soil colloid is the storage part, or the part of the soil where these nutrients are stored. So when the plant nutrients are in the soil colloid, it means that they are not available for plant absorption. But once they enter soil solution, then they become available for plant absorption. Now, when soil pH is considered, we say that this is very important because it determines, soil pH determines availability of plant nutrients. So here I'm talking about availability of plant nutrients. It means it's the one which determines what plant nutrients now are available for plant absorption. For example, most of plant nutrients are available at this pH range, about 6.5 to 7.5. So most of plant nutrients are available. But out of this range, most of plant nutrients are found in or absorbed on the soil colloids. So it means that they are not available for plant absorption. For example, phosphorus. Phosphorus is if the pH is less than this one, that is 6.5, phosphorus will not be available for plant absorption. So one of the significance of soil pH is to determine the availability of soil of plant nutrients. Another significance is also special for it gives us the ability to choose the right crop in a certain particular land. Now, if we want to grow a certain crop, you have to consider this, because each plant has its own soil conditions or soil condition favorable for its growth. For example, tea crop is grown in acidic soils, while the cotton does well in alkaline soil. So this is very important in case of identifying the particular crop to grow in a particular piece of land. Another one is it affects microbial activities. Microbial activities. Now these are very important organisms. For example, decomposers, which decompose remains of plants and animals to add soil organic matter, which is rich in plant nutrients. Then soil pH also determines their activities. Too acidic soils lowers the microbial activities. So it means if the soil pH is less than this range, you find that most of the decomposers will not do well. Not only decomposers, there are other microorganisms or microorganisms like bacteria, which are very important to fix nitrogen. For example, Nitrobacter, Nitrosomonas, also they work well in a certain range of soil pH. So that is another significance. So these are some of significance of the soil pH. To, as I said, to determine the availability of plant nutrients. The second one, it enables us to choose the right crop in the right piece of land, and also it affects soil pH affects microbial activities. Question number 7b. Aluminium ions hydrolyzes. Why are aluminium ions not considered as a soil base, although it is a cation? Why aluminium? Aluminium ions, though they are cations, still they are not considered as soil bases. Instead, we consider it as an acid. Even in determining the percentage base saturation of the soil, normally hydrogen ions as well as aluminium ions, though they are cations, still they are considered as acids. Now the reason here is because aluminium ions hydrolyzes. So it means reacts with the water because of its small size. So it reacts with the water molecules to form aluminium hydroxide, then plus hydrogen ions. Now, in the presence of water, aluminium ions, for example, in the soil solution or soil water, you find that aluminium, because of its small size and the presence of empty orbital, it hydrolyzes or it accommodates lone pair of of water molecules, then you end up with the formation of aluminum hydroxide as well as the hydrogen ions. So the hydrogen ions are the ones which determine the soil acidity. That is why aluminum ions, though they are cations, still they are not considered as soil bases. Question number 7C. Question number 7C. What are the negative effects of the following practices on soil? What are the negative effects of the following practices in the soil? Practices in the soil. Now, one is the effect of overliming. Effect of overliming. Roman 1 is overliming. Overliming. Now, liming, this is the process or is one of the methods used to regulate soil pH. Is the addition of a lime or liming material. And what are these liming materials? Normally in agriculture, we use silicates, carbonates, hydrogen carbonates, and the oxides of magnesium and the calcium as liming materials. So this liming process is used to moderate or to raise the soil pH, to remove or to correct soil acidity, to raise the soil pH by removing soil acidity. So it means this is the addition of bases in the soil. And basically, the bases which are commonly added are magnesium and the calcium in the form of carbonates, hydroxides, oxides, and the silicates. Now, during this process, so it means if you overline the soil, so it means you will raise the soil pH. So this will raise the soil pH, soil pH. So the soil will be more basic. The soil will be more basic in such a way that it can affect or it can go out of this soil range, favorable for crop production. So the effect of overliming is to increase the soil basicity, which can go out of the required soil pH range. Another practice is heavy irrigation. The effect of heavy irrigation in the soil. Heavy irrigation. Now this also can happen if it rains heavily or heavy raining. Heavy raining also can result into the same effect or bring the same effect as in heavy irrigation. Heavy irrigation leads to leaching. Leaching, this is the downward movement of soluble bases. So the bases like potassium, sodium, calcium, which are essential for plant growth, then they can be taken deep in the soil and be out of reach of soil of plant roots. Then they will not be available for plant absorption. So soil irrigation or heavy irrigation, this lead to leaching, which will increase. This will result into increase in the soil pH and in the soil acidity. Increase in the soil acidity. Because most of bases will be taken deep in the soil. So on the top soil, where mostly where crops obtain their required nutrients, then they will be less available. So this is another practice which can affect or bring negative effect to soil. So this will increase the soil acidity. Another one is burning of vegetation. How burning of vegetation can affect the soil for crop production. Burning of vegetation can result into first removal of some nutrients in the form of gases. For example, phosphorus can be, or nitrogen can be taken away as the oxides of these elements and will be lost. So it means soil will lose some of its nutrients. Also, this can destroy useful microorganisms. Can destroy useful microorganisms like decomposers. Microorganisms can destroy some of microorganisms. And also, burning of vegetation can destroy soil structure. Can destroy soil structure because soil with a good structure is favorable for crop production. It will be rich in nutrients and also it will have good aeration, good drainage, high water holding capacity. So if soil structure is destroyed, also it brings a negative effect. Then another effect of this burning of vegetation can lead to soil erosion because of removal of top or the soil cover. Then it can result into soil erosion. Another practice is the application of ammonium sulfate. Application of ammonium sulfate. Ammonium sulfate, this is a nitrogenous fertilizer. Nitrogenous fertilizer. Now, if excessive application of ammonium sulfate is done in the soil, then this can result to increase the soil acidity. So can increase the soil acidity. Can result into increase in soil acidity. So the soil pH will be lowered. So it will go out of the required range. Why? Is it because ammonium ions, once the ammonium sulfate is applied in the soil, then it will form ammonium ions. Then in the presence of soil water, then this will end up with the formation of ammonia, which will be given out, and the hydrogen ions. So these hydrogen ions are the ones which will lead to soil acidity. So these are the negative effects of these four practices, which can be, if they are not controlled, then they can bring negative effects to the soil. So that is, now we go to question number 8. Question number 8. This is question number 8. Is the question from the topic of chemical equilibrium. So this is a question under chemical equilibrium. Now, question number 8A. The question tells us that there is only one value of the equilibrium constant for a particular equilibrium system at a particular temperature, but there are an infinity number of equilibrium positions. Explain. There is a fixed or one value of equilibrium constant at a particular temperature. Still, there are an infinity or many equilibrium positions. Now explain. Normally, chemical equilibrium is achieved at a constant or given temperature. So this one, once a chemical reaction achieves its equilibrium position or its equilibrium point, then the equilibrium concentrations of reactants and the products remain constant. Now, for the equilibrium position, depends on concentration and on the concentration. So the reason here is because equilibrium positions depend on concentrations depending on the concentration. So it means varying or changing of concentrations, then changing of concentrations affects the position of equilibrium. So as according to Lyakhatelli's principle, that if any equilibrium or chemical equilibrium has achieved its equilibrium point or position, now if you introduce an external factor, or if we change an external factor, then the position of equilibrium will change in order to eliminate that effect. Now, why this position of equilibrium changes is for the purpose of maintaining equilibrium constant. So every chemical equilibrium system at a particular or constant temperature, its equilibrium constant it remains constant. If the equilibrium point is achieved for any chemical reaction at a particular temperature, then this equilibrium will remain constant. But by changing some factors, for example concentration, if the reaction involves gases, if we change the partial pressures or you affect the pressure of these gases, then the position of equilibrium will change. And also, if you change the temperature of the reaction, depending on type of reaction, if the reaction is exothermic or endothermic, also the position of equilibrium will change. So we say that the equilibrium constant is constant at constant temperature. So the equilibrium constant is affected only by temperature. But if the temperature remains constant, the equilibrium constant value will remain constant. But only equilibrium position will change because equilibrium position depends on external factors such as temperature, concentration, as well as pressure if the reaction involves gases. So the positions of equilibrium depends on temperature or on external factors like a concentration change, but equilibrium constant is constant at a constant temperature. Number 2 says that, or Roman 2, question number 8A, Roman 2. Changing the pressure in a rigid reaction vessel by changing the volume may shift the position of a gas phase equilibrium, whereas changing the pressure by adding an inert gas will not. Why? Now, if you have a rigid vessel, so it means the vessel that does not change its volume, it is rigid, but you can change the pressure by adding more gaseous component, and also you can change the pressure, internal pressure of the system by adding inert gas. Now the question is, changing the pressure in a rigid reaction vessel by changing the volume may shift the position. How do we change the volume? So it means in a gaseous equilibrium system, normally we can change the position of equilibrium in three aspects. One, we can change the position of equilibrium gaseous equilibrium system by adding or by changing the volume of the container. But according to our question, the container volume or the container is rigid, so it means it cannot change its volume. Instead, by changing the amount of gas. For example, if it is a gaseous reaction, let's say hypothetical gas A plus B, then if these two gases form equilibrium with the gas C. Now this is the system. If you change the amount of reactant gases by increasing their pressures or amounts. So it means you will be also increasing the partial pressure, and then you will favor forward the reaction. If you decrease their partial pressures by decreasing the amount, also you will favor backward the reaction. But if you add inert gas, no effect will be noted. Why? Is because an inert gas is neither reactant nor product. It is neither reactant nor product. So it means the addition of inert gas will increase the total pressure of the system, but will not affect the position or will not change the position, because it is not either a reactant or product. So it means even if an inert gas will be added, no reaction that will occur. As a result, the equilibrium position will not be affected. The equilibrium position will not be affected. Now, question number 80C. 80B. That is 8B. 8B. 8B says, for the reaction of the type AB dissociates or decomposes to form A and B, show that if at a particular temperature AB is 1/4 dissociated, the total pressure is 15 times its equilibrium constant Kp. Now, if you have this type of reaction, AB gas, if it dissociates partially to form gas A and the gas B, then the question says, if gas AB at a particular temperature or fixed or given temperature, now if it is 1/4 dissociated, the total pressure of the equilibrium system will be equal to 15 times the equilibrium constant Kp, or the equilibrium constant in terms of partial pressure. So here we have we can draw or show like this. Here we have total moles. Then now in this one we have initial moles. Now we assume the initial mole to be 1. So here is 0, total moles is 1. Before reaction, there are no products. That is why the number of moles are 0. So the number of moles of A and B are 0. Then change in moles during chemical reaction. Change in number of moles. Now, during chemical reaction, reactants decrease while the products increase. So here we assume that X moles of A are reactive or are converted to product. So we take minus X. Now, because the reactants are increasing, so here is a plus X, and also here is a plus X. The total moles here is a plus X. Then equilibrium moles. At equilibrium, now equilibrium moles. So here is 1 minus X, here is a X, here is X. The total moles is 1 plus X. So you can start with any number of moles. Any number of moles. Can be 1 mole, 0.5 moles, 0.2, 5 moles, 100 moles. But here we decided to start with the 1 mole. Now the question says, if 1/4 of AB, so it means 1/4 of this 1 mole initially present changes or dissociates, it means that this change is the amount mentioned. It is 1/4. So this is 1/4 of 1 mole. So the 1/4 of 1 mole is is a quarter. So the value of x is equal to a quarter, which also is equal to 0.25. So this is the value of x. So the value of x. Now let us calculate the number of moles. So number of moles, we start with the moles of number of moles of AB. Number of moles of AB is equal to 1 minus x, which is equal to 1 minus a quarter, which is equal to 3/4, or we can say 0.75. So these are equilibrium moles of AB. Then number of moles of A also is equal to number of moles of B, which is equal to x, and this is equal to 1/4 or 0.25. So these are number of moles. Then total moles. This is equal to number of moles of AB plus number of moles of A plus number of moles of B. So this is the total number of moles at equilibrium. So this is equal to 1, then plus x, then we get 5/4, or it is 1.25 mole. 25 mole. So this is the number total moles. Now let us calculate the mole fraction of each gas component. Mole fraction in the equilibrium. So mole fraction we can take. Now the mole fraction, normally we abbreviate it by using capital letter X. So mole fraction of AB is equal to number of moles of AB divided by total moles. This is equal to 0.75 divided by 1.25, which gives us, or you can take this one, which gives us a 0.6. The mole fraction, or the number of moles, or mole fraction of AB. Mole fraction is 0.6. It is 0.6 or 3/5. Then mole fraction of A is equal to mole fraction of B, which is equal to 0.25 divided by 1.25. This gives you 1. It is 1/5, or it is 0.2. So these are mole fractions. Now after that, we go to partial pressure of each gas component. Partial pressure of each gas component. So the partial pressures. Normally partial pressure is given by the product, or as the product of mole fraction of a given gas times the total pressure of the system. So let the total pressure be PT. So the mole fraction, so the partial pressure of AB is equal to mole fraction of AB total pressure. This is equal to 3/5 PT, or it can be 0.6 PT. So this is the total, this is the partial pressure of AB. Now partial pressure of A is equal to partial pressure of B, which is equal to mole fraction times the total pressure. This is equal to 1/5 total pressure, or 0.2 total pressure. So these are the partial pressures of 3 gaseous components. That is A, B, A, and B. A, B, A, and B. So the last one is a KP expression. So the equilibrium constant Kp in terms of partial pressure is given as the Kp value is equal to partial pressure of A, that is the product, times the partial pressure of B, another product, divided by partial pressure of AB, that is the reactant. So this is equal to 3 over, so this is equal to 1 over 5 Pt times 1 over 5 Pt divide by 3 over 5 Pt. So this is equal to Pt squared over 25, then you divide by 3 over 5, this is a Pt. So this is equal to Pt squared over 25 times 5 over 3 Pt. So this and this one cancel here, will remain with 5. So this is Kp is equal to, so Kp is equal to, this is equal to, here is Pt over 15. So therefore, total pressure of the system is equal to 15 equilibrium constant in Kp. So this is shown or proved. So that is our answer for the question number 80B. For question number 80B. Now question number 80C. Question number 80C. Question number 80C. The question says, the following equilibrium is set up in a solution by dissolving cobalt-2 fluoride crystals in water to form pink species, that is a complex compound, and then adding concentrated hydrochloric acid until the solution becomes blue. Until the solution becomes blue. So we have this equilibrium system that is a complex. This is a cobalt. Then we have 6 water molecules as a ligand. The overall charge is a 2 positive. Then plus 4 chloride ions from hydrochloric acid. But these two reactants form equilibrium with another complex that is cobalt, then chloro. There are 4 of them. Here is -2 aqueous, then plus 6 water molecules. Now this is a blue in the color, while this is a pink in the color. So the solution, first solution made before addition of hydrochloric acid is pink. That is the complex formed after dissolving cobalt-2 chloride in water. Then after adding hydrochloric acid, then the solution changes from pink to blue. Now this is an equilibrium system. And normally an equilibrium system is achieved or is attained at a constant temperature. It will remain constant unless the temperature is changed. Except the equilibrium position can change. If we introduce any external factor like concentration, temperature, but if the equilibrium temperature remain constant, then the equilibrium also remain constant. And know that, or remember that equilibrium constants or equilibrium systems are dynamic. They are not static. They are dynamic. That is why they can change their position depending on external factors like concentration change, temperature change, pressure change if the equilibrium system involves gases. So the equilibrium system is dynamic. It is never stationary. it is dynamic. That is why once you introduce any external factor as according to the Cartesian principle, it changes its position to show that it is not stationary. It is dynamic. Now, question number 1. Question Roman 1. Roman 1 is that, does the reaction cease when the solution becomes blue? Remember I said this equilibrium system was formed by first dissolving cobalt 2 chloride crystals in water. Then the pink solution was formed. Then hydrochloric acid, which is the source of chloride ions, was added. Then the equilibrium system was established between this complex and this one. Then if this equilibrium is achieved, now the question is, does the reaction cease when the solution becomes blue? So when the solution becomes blue, it means the equilibrium has been achieved. Equilibrium point or equilibrium point has been achieved. As a result, we say the equilibrium system is dynamic, so the equilibrium will not cease. So the equilibrium will not cease. Will not cease. Why? Because the equilibrium system is dynamic. Because the equilibrium system is dynamic. It is never stationary. It is dynamic. That is one. The second question is, the forward reaction is endothermic. Explain the color change observed on cooling the reaction mixture. Now, remember, when we consider heat or the temperature as one of the factors which can affect equilibrium position, we have to consider the type of reaction in relation to heat change. Does the reaction absorb or lose heat? Does it absorb or lose heat? Now, according to our question, the question says our reaction is endothermic. Now, for the endothermic reaction, heat is a particle